Hello guys, welcome to Silicon Glyph. So this is a new series where we're going to learn about Verilog coding. So Verilog is also one of the HDLs which we use to describe the hardware circuits like digital circuits mostly. So we have already seen the VHDL tutorials and I'm going to resume them soon actually because there is a lot of things we have to do in VHDL. I stopped at a certain point but I'm going to resume it again. So this series is basically only for Verilog. So Verilog, as I said, Verilog is also a HDL, but Verilog is a bit easier than VHDL, and Verilog looks almost like your modern languages, like software languages. So coming to this video, we are going to implement a logic gate AND gate in this video. So to install this software, I've already made a video on how you can install this software. This software is Xilinx Vivado and it is free. So you can install this in your PCs and you can basically code in VHDL or any HDL basically. So if you're wondering if Verilog or any HDL is difficult, it is not really that difficult because if you have a better understanding in digital logic design, then Verilog and VHDL and any HDL basically is easier. So if you don't know digital logic design, I recommend you to learn the digital logic design first and then jump to these HDL languages. So if you are wondering why these HDL languages are useful, is these HDL languages are used to design your integrated circuits. Like if you want to design a processor, you can do it in a Verilog and VHDL, and you can also simulate your models, whatever design you did, you can actually simply simulate it and check your outputs. I've already told you how you can create projects and how you can initialize all these inputs and files and stuffs in the video. I will put the links in the description below. You can just follow them and see the watch those videos for better understanding. So coming back to the Verilog, in Verilog, everything is done inside a module. So you can see that we have defined a module using the keyword module and followed by our module name. And then we will end the module using end module keyword. And then you define the ports, input and output ports inside the module definition. Now, how can you send the data from one port to another port? So we have inputs and outputs. We will do the logic inside our module and we will send the output. So basically, there are two things in Verilog. One is called as wire and another one called as register. So think of wire as an electrical wire. So what does an electrical wire do? Electrical wire will send the signal from one component to another component. The only purpose of wire is to send the data from one component to another component. Won't store anything. It won't store anything and it will just drive whatever you give, whether it's 0 or 1. It will just drive the input and it will simply send it to the uh, other end. But register will store the data whenever the data is you know given to the register. So we use both wire and register in Verilog and they are very important. So when we define the input ports and output ports here, these are basically wires because we didn't specify anything here. So we consider these A, B and Y as wires. So how can you send a data through wire in Verilog? We use a keyword called assign for this. So assign your your variable name. In our case, we are performing an AND operation. That means we will perform an AND operation for both the inputs and send the output to Y. So here the Y is the output. So we are going to send the data to Y. So for this we use assign followed by Y is equals to. So what data should Y should drive? Which is A and B. We use ampersand for bitwise AND operation in Verilog. In VHDL, we follow the keywords called AND or NOT, etc. But in Verilog, we use symbols. And for NOT operation, we use the vertical line. And then for XOR operation, we use the power symbol. I don't know what this, cap-like symbol. Let me show you this symbol. So we use this for bitwise XOR, and for NOT, we use this symbol. So this module performs the AND operation. So I'm going to use ampersand. So that now what this statement means is will perform A and B and sends the output to Y. And if the Y is a wire, then we use assign statement to send the data. If the Y is a register, you cannot send the data directly inside a module. We have to use procedural blocks like always, if else, case, etc. So we are going to see them in the next videos, but for this video, we are going to see wires only. So now as we return the source code, we have to write the test bench for this, the same process, create file. We can basically give any name here. So this is the file name. So I'm just defining as that logic gates underscore test bench. Then finish. If you don't define any ports in test bench, because test bench don't have any ports, it just tests your modules. So I'm not going to define any ports, and I will simply go OK. And now we have the test bench, right? If it asks you something like you didn't define any ports, shall I continue, or something like that, if the dialog appears, you simply click on S and you define your test bench yourself, like module followed by your test bench name, and then you don't define any ports inside this brackets, and then end module. And inside this module we write the uh, truth table. So coming to the truth table is important when you're writing a test bench, because truth table is a table which says at particular inputs what will be the output. So let's say we have AND gate. So if you take the conditions, we have two inputs A and B. So how many combinations we will get? 4. So 0 0, 0 1, 1 0, and 1 1. So for these inputs, what will be the output? Y. When you have complex circuits, you can use these truth tables to create a logic function. But in our case, it just an AND gate. So this is the logic function A and B. That means if both the inputs A and B are 1, then output Y will be 1. So to do this, basically what we do is in test bench, we will store the inputs and we will drive the output. So remember the words I'm saying, we will store the inputs, we will drive the output. So the input should be registers. I'm going to define it as ATB and BTB. And then the output will drive. So wire YTB. So A and B are the inputs and Y is the output. So we define it this way, and now we specify which module we are going to test. We are going to test the AND gate. So I'm going to simply write AND gate UUT. So what this statement means, we are going to test the AND gate, and we are defining AND gate module as a unit under test. UUT stands for unit under test. So what we basically saying to the simulator simulator is that you define the AND module, but you have to simulate it. Now we have to port the maps, and you can do it in a two ways. You can do it directly by giving these values directly in order. So here A, B, Y is the order. So you can simply write A underscore TB, B underscore TB, and Y underscore TB. But imagine a case where you have a lot of ports and you have to define them by order. You don't remember the order when you have a lot of ports. So what we are going to do is we are going to specify which port inside your test bench is equivalent to which port is inside your source module. So in here we have input as A and B. So we have to specify what A means in the test bench. It is a bit confusing when I say directly, and if I write here, you will know. So to port, we use dot A. That means dot A port in AND gate. That means this port is equals to, if I put A TB here, The port A in AND gate is nothing but A TB in logic gate. So we are giving A TB to the port A of AND gate. Same with B, TB, and same with Y. When you're defining the ports this way, you don't need to follow any um, any order. So you can simply go here and then you can simply do this. I'm going to save this file. Didn't It didn't update, that is why I'm getting the error. So when I'm saved the file, I didn't get it. Oh wait, so the error basically happens because I didn't put a dot here. Yeah, I didn't see that. So when you're sending the data this way, you should always see if you are missing something. I missed a dot here, and that is why the error kept occurring there. So now we have defined our test module, and then we will assign the values for A and B. For this, we are going to use an initial block in which we are going to send the data inside A and B. So initial, begin, end. The syntax actually looks more like a MATLAB syntax, right? Anyways, now we are going to send the data inside A, TB. To send direct data, this is the syntax. Remember this syntax because we are going to use this in almost all test benches. So ATB, you can either use 0 or less than 0, but I prefer using less than 0 because this is another concept I'm going to explain in the future videos why we are using less than, equal to, and not just is equals to. So now I'm going to say the size of data, and that means how many bits the data will be. So in our case, it will be a single bit, so 1, and we have to put the column. What is that? Is that column? I think it is a first single quote. Yeah, single quote. So we have to put a number of digits and then single quote, and then we will define the what number system we are using. If you are using a binary, and we have to use B. If you are writing the data in decimal, we use D, hexadecimal hex, and octal is O. So we are going to send the data as binary. So I'm going to put B, and then now we have to define the data. In our case, it is 0 because in truth table 0, 0. So the first case will be 0, 0, right? So I'm going to put 0. If you are sending a decimal data, we have to put D 0. Now this will convert this 0 decimal 0 into binary, and which is 1 bit. As it is 1 bit, we can simply define it in binary, and then B TB 1 bit binary 0. I'm just going to copy this, and then I will paste it in 4 times because we have 4 cases here, right? And finally 1, 1. So if you observe clearly, we have a problem here because we didn't give any delay. We have simply defined the variables, values for A and B, and we simply write it here. There is a small problem here because as we didn't give any delay, the values of A and B will change very quickly, and we cannot see the difference. If I run the simulation, you will see the difference of the importance of delay. So it will take, okay, so it actually run a bit quicker. So now if I see this, you can see that the values are not starting with 0, 0, but it's starting with 1, 1. The only reason that explains this is you didn't define any delay here. You didn't give any delay for every case. So so it will change from 0, 0 to 0, 1, and 0, 1 to 1, 0, and it will change from 1, 0 to 1, 1 very quickly, and it will stay at this because we define them as registers basically. So it will just be in here for every case because these 3 conditions are shifted very quickly, and it will go for the final case. So to avoid this, we will use a delay. And to put delay, we use syntax called hash followed by your time period. So in our case, we are going to put 10 nanoseconds delay. So I can simply put it as hash 10. So for every values, I'm going to put 10 nanoseconds delay. So hash, oh wait, 10. And now another one, hash 10. Now this test bench has a delay of 10 nanoseconds per each, each case. So I'm going to save the test bench and let it update. If you click on run simulation when it is showing the update here, you will get an error. So if you don't worry if you get those errors, just click on OK and then click run simulation again. Now you can see the simulation once it's done. Right now it is done. I'm going to minimize this so we can see. So if you click on this thing, it will just fit your waveforms to this graph. So now we can see that the values are actually changing here, but you cannot see them clearly. So what I'm going to do is I'm going to zoom these. You can either click on this by putting the marker, this marker here, and then you can simply click on plus to zoom in, or you can also use another method in which we simply click on the waveform anywhere in the waveform, and then you just drag your this red color thing. You can just drag your mouse to the some point, and then if you leave it, it will zoom the uh, marked wave. So you can now see the inputs. For 0 0 we got output as 0, and for 0 1 output 0, 1 0 output is 0, and 1 1 output is 1. And this basically matches the truth table of AND gate. So this is how you see the outputs. So now we have uh, simulated our logic function, and this is how you basically do operations in Verilog. So that's it. That is it for this video. And in this video, we have seen how you can define modules, how you can use voice and registers, not registers. We have only seen voice here. Maybe in the next video, we are going to see about registers and how you can use registers. And you have seen how you can assign the values to a wire and how you can write the test benches and create the test benches. And you have also seen how you can simulate. So that's it for this video. And in the next video, we are going to go in depth about registers, and we are going to create some more logic circuits. And thank you for watching. If watching this video up to this far, and thanks for the support so far. Thank you.